There is a number that should not exist, and I need you to understand why it should not exist before I can tell you what it means. Because what it means is the kind of thing that changes how you think about everything. And I do not say that lightly. I have spent the last month on this channel building toward this moment, and if you have watched the previous videos, you already sense where this is heading. But I promise you, you do not. Not yet. In 2023, a team at Northwestern University measured a property of the electron called its anomalous magnetic moment. This is a measure of how the electron wobbles in a magnetic field, and it depends on virtually everything in quantum physics. Every virtual particle that can pop in and out of the vacuum contributes to this wobble. Every force, every field, every interaction leaves its fingerprint on this single number. To calculate it from theory, you need quantum electrodynamics, and you need to evaluate Feynman diagrams, those little line drawings that represent particle interactions. At the lowest level of approximation, there is one diagram. At the next level, 7. At the next, 72. By the time you reach the 10th order, there are 12,672 diagrams, and each one requires a separate integral that can take months to evaluate on a supercomputer. A Japanese physicist named Toichiro Kinoshita spent the better part of his career at Cornell computing these diagrams. He started in the 1960s. The 10th order calculation was completed in 2012. That is roughly 50 years of work on a single prediction. And when the Northwestern team measured the electron's magnetic moment in the laboratory, using a single electron trapped in a Penning trap, cooled to near absolute zero, the result agreed with the theoretical prediction to 13 decimal places. 1.001-159-6521-8059. Theory and experiment, matching to better than 1 part in a trillion. Think about what that means. Not just the precision, although the precision is staggering. If you measured the distance from New York to Los Angeles to that precision, your measurement would be accurate to less than the width of a single human hair for a continent. That is how precisely they measured one electron. But think about what kind of thing mathematics would have to be for this to happen. A set of equations written down by humans on paper, using symbols that humans invented, predicted a property of a subatomic particle to 12 decimal places before anyone went into a laboratory. That is not how a tool behaves. A hammer does not know what the nail will look like before you swing it. A ruler does not predict the length of a thing it has never measured. But mathematics does, routinely. And nobody can explain why. This is the question that the physicist Eugene Wigner asked in 1959, and it is the question that nobody has answered in the 67 years since. Wigner was not a philosopher fishing for attention. He was a Nobel Prize-winning physicist, one of the architects of nuclear reactor theory, a man who had worked on the Manhattan Project, and in May of that year, standing in front of an audience at New York University, delivering the inaugural Richard Courant Lecture in Mathematical Sciences, he chose a title that the physics community has been quietly uncomfortable about ever since: the unreasonable effectiveness of mathematics in the natural sciences. And the word that matters in that title is unreasonable, not remarkable, not impressive. Unreasonable, as in, there is no rational explanation. Wigner opened with a joke. 2 old high school friends run into each other. One has become a statistician. He shows his work, and in the equations there is the symbol pi. His friend says, "Wait, pi? the ratio of a circle's circumference to its diameter. What does a circle have to do with population statistics? And the statistician cannot really explain it. Pi just showed up. It was not invited. It just turned up in the math. The way it turns up everywhere, from the Heisenberg uncertainty principle, to the normal distribution, to Einstein's field equations, to the behavior of a river's meandering, a number defined by circles appearing in equations that have nothing to do with circles. Wigner went further. He noted that it is not at all natural that laws of nature exist, much less that man is able to discover them. He observed that Newton's gravitational law, based on very scanty observations and containing the concept of a second derivative, which is not a very immediate concept, has proved accurate beyond all reasonable expectations. He noted that quantum mechanics was formulated in complex Hilbert space with Hermitian operators, structures that are far from natural or simple and cannot be suggested by physical observations. And yet this framework proves close to being a necessity in formulating the laws of quantum mechanics. He cited the helium atom's lowest energy level, agreeing with experiment to 1 part in 10 million. He cited the Lamb shift agreeing to better than 1 part in 1,000. And then he closed with what I personally think is the most haunting line in any physics paper of the 20th century. He said we are in a position similar to that of a man who was provided with a bunch of keys, and who, having to open several doors in succession, always hit on the right key on the first or second trial. Imagine that, door after door after door, and the key always fits. At what point do you stop calling that luck? At what point do you admit that something else is happening? Wigner himself is worth knowing about, because his biography illuminates the question. He was born November 17th, 1902, in Budapest as Wigner Jenő Paul, one of the extraordinary Martians of Budapest, that improbable cluster of Hungarian-born geniuses, Leo Szilard, John von Neumann, Edward Teller, Denis Gabor, Paul Erdos, who reshaped 20th century science so dramatically that their colleagues joked they must be aliens. His mathematics teacher at the Fasori Evangelicus Gymnasium was Laszlo Ratz, and Wigner later said no one could evoke the beauty of the subject like Ratz. He kept Ratz's photograph in his workroom for the rest of his life. Von Neumann was 1 year behind him at the same school, under the same teacher. One high school, one city, two of the most important scientific minds of the century. Here is a detail I think matters enormously. Wigner was trained as a chemical engineer, not a mathematician or physicist. He got his doctorate at the Technische Hochschule Berlin in 1925. He drifted into physics through the Wednesday colloquia, where he encountered Planck, Einstein, and Heisenberg. His sister Margit married Paul Dirac in 1934, so Wigner liked to call Dirac my famous brother-in-law. He won the 1963 Nobel Prize. His first wife, Amelia Frank, died of cancer on August 16, 1937, less than 8 months after their wedding. He was devastated. About his peers, he wrote that he had known many intelligent people, but none with a mind as quick as von Neumann's. But Einstein's understanding was deeper even than von Neumann's, both more penetrating and more original. When Wigner won the Nobel, he said he never expected to get his name in the newspapers without doing something wicked. He died January 1st, 1995, at 92. His essay, the one he delivered that May afternoon in New York, remains unanswered, and his essay, for all its fame in physics circles, has a quality that most summaries miss. It is not triumphant. It is not celebrating the power of mathematics. Read carefully. It is bewildered. Wigner is not saying, "Look how great math is." He is saying, "This should not be happening, and I cannot figure out why." He describes the situation as a gift we neither understand nor deserve, and says we should be grateful for it and hope that it will remain valid in future research. That last phrase haunts me. Hope that it will remain valid. One of the greatest physicists of the 20th century, a man whose entire career was built on the effectiveness of mathematics in physics, expressing hope, not confidence, that the pattern will continue, as if he suspects it might be too good to be true, as if whatever is behind this effectiveness might be something fragile or something that operates on terms we cannot access. And nobody has improved on his position since. Richard Hamming, the mathematician who gave us error-correcting codes, wrote a response paper in 1980 in the American Mathematical Monthly, offering 4 partial explanations. We see what we look for, so we find math that works. We select the math that fits and ignore the rest. Math only addresses a limited part of reality, and evolution shaped our brains to detect patterns. Then Hamming admitted that all 4 explanations combined are still not sufficient. The mystery remains. Mark Steiner wrote an entire book in 1998, The Applicability of Mathematics as a Philosophical Problem, arguing that the way physicists use mathematical beauty and analogy to discover physical laws reveals a universe that is user-friendly in ways that should alarm anyone who takes naturalism seriously. The universe cooperates with our mathematical intuitions far more than any naturalistic worldview predicts. This has been published, debated, and discussed for decades, and the result is Wigner's original observation restated in increasingly technical language. Nobody knows. Now, some physicists have taken this mystery further than Wigner dared. There is a growing contingent that believes math does not describe reality, but is reality, that the physical universe is itself a mathematical structure, and we are inside it. I want to set that aside for now, but I want you to remember it, because we are going to come back to it, and when we do, you are going to wish we had not, because the electron's magnetic moment is not an isolated case. It is not even the most disturbing case. It is just the most precise. The real horror show, the thing that should have made front-page news in every country on Earth, and somehow did not, is the pattern of mathematics, knowing things about reality before reality has revealed them, predicting the existence of things no human has ever observed, years or decades or centuries before confirmation. This pattern has been repeating since the 1860s and has never once failed. And nobody can tell you why. On January 2nd, 1928, Paul Dirac submitted a paper to the Proceedings of the Royal Society. He was 25 years old. He was trying to fix an aesthetic problem. The Klein-Gordon equation that described relativistic electrons was second order in time, which clashed with the rest of quantum mechanics. Dirac wanted an equation that was first order in both time and space. He wanted beauty. He wanted mathematical elegance. To make the equation first order, he needed to take the square root of the energy-momentum relation E squared equals P squared C squared plus M squared C to the fourth. And when he did, the mathematics demanded something unexpected. The equation required 4x4 matrices, expanding Pauli's 2x2 spin matrices into what are now called gamma matrices. And the solutions to this equation came in 2 flavors. Positive energy solutions, which described electrons behaving exactly as observed, and negative energy solutions, which described something that should not exist. Dirac's first instinct was to throw them away. Negative energy particles are not a thing, but the math would not let him. The equation was not a buffet where you could take the parts you liked and leave the rest. The positive and negative solutions were two faces of a single mathematical structure. Accept one and you are logically committed to the other. Dirac tried to explain them away. In 1930, he proposed the Dirac Sea, an infinite ocean of negative energy electrons filling every possible state. So the only observable thing would be a hole in that sea, a bubble of missing negative energy that would appear as a positive particle. He tried to identify these holes as protons, which was desperate and wrong, and he knew it, because the math demanded the holes have the same mass as the electron, and protons are roughly 1,836 times heavier. By 1931, Dirac gave up trying to make the math say something comfortable and accepted what it actually said. There exists a particle identical to the electron, but with positive charge. He called it the anti-electron and predicted it in a published paper. On August 2nd, 1932, Carl Anderson at Caltech photographed one. He was studying cosmic rays. He was not looking for Dirac's particle. He found 15 anomalous tracks in roughly 13,000 cloud chamber photographs, tracks curving the wrong way in a magnetic field, a 63 mega-electron volt positron. The anti-electron was real. Matter has a mirror image, and the only reason anyone knew to look for it is that an equation, written on paper by a 25-year-old who wanted his math to be pretty, said it had to exist. I want to be precise about what happened here. Dirac did not start with a physical hypothesis about antimatter and build math to describe it. He started with math. He started with aesthetic criteria, and the mathematics contained information about reality that no human possessed. The math knew something nature had not yet revealed. Dirac won the Nobel in 1933. Anderson won it in 1936. Dirac took from this a philosophical position he held for the rest of his life. On a blackboard at Moscow University in 1956, asked to write his philosophy of physics in one sentence, he wrote, "A physical law must possess mathematical beauty." In 1963, he said it is more important to have beauty in one's equations than to have them fit experiment. That sounds insane, but Dirac had earned the right to say it. Mathematical beauty had shown him antimatter before any instrument did. He was not being mystical, he was being empirical. The beauty had been a reliable signal, and the deep algebra underneath his equation, Clifford algebra, had been created roughly 50 years earlier by W.K. Clifford, extending Grassmann's work from the 1840s, pure mathematics, no physical application intended. The mathematical tools Dirac needed already existed, sitting in libraries, built for beauty, waiting for reality to need them. Let me tell you something about Dirac the person, because it matters for understanding what mathematical beauty meant to him and why he trusted it over experiment. Dirac was famously, almost pathologically, quiet. Stories about his silence are legendary in physics. When Niels Bohr complained that he could not find the right word to finish a sentence, Dirac said, "But why do you want to finish it?" His colleagues at Cambridge reportedly invented a unit of measurement called the Dirac, defined as 1 word per hour. He was asked once if he had any questions after a lecture and replied, "That was not a question. It was a statement. He was estranged from his father, Charles Dirac, a Swiss-French teacher who enforced a brutal rule at the dinner table. Young Paul was only permitted to speak in French, since his father was a French teacher, and if he could not find the right French word, he was required to remain silent. Dirac later attributed his extreme reticence to this childhood rule. He never spoke at dinner because he could not find the words. And yet, this almost mute man, this person who struggled with the most basic human communication, possessed a mathematical intuition so profound that it borders on the inexplicable. He did not arrive at the Dirac equation through laborious calculation or by following the standard methods of the time. He guessed. He made an inspired, aesthetically motivated leap to a form of the equation, and then worked backward to justify it. The beauty came first, the proof came second. This is not how science is supposed to work. You are supposed to start with data, form a hypothesis, test it, and refine. Dirac started with an aesthetic conviction about what the equation should look like, and the equation turned out to contain information about the physical universe that no human had ever suspected. A man who could barely speak discovered antimatter because he trusted mathematical beauty more than experimental evidence. And he was not alone in this. Julian Schwinger, who calculated the first quantum electrodynamic correction to the electron's magnetic moment, the alpha over 2 pi result that agreed with experiment to 6 decimal places, had that result engraved on his tombstone. Not his name, not his dates, not his Nobel Prize. The formula, alpha over 2 pi. That is what he wanted remembered. The beauty of the result. As if the formula were more real than the man who derived it. But Dirac's equation was at least built for physics. He was trying to describe a physical electron. The deep algebra was borrowed from pure math, but the equation itself was purposeful. So let me escalate. Let me tell you about Maxwell. James Clerk Maxwell published his unified theory of electromagnetism in 1865, having read it to the Royal Society the previous December. His equations predicted that oscillating electric and magnetic fields should propagate through space as waves at a speed calculable from 2 known constants, the permittivity and permeability of free space. Maxwell did the calculation. He got approximately 310,740 kilometers per second. The known speed of light was approximately 315,000. Agreement within 4%. Maxwell concluded that light itself is an electromagnetic wave. But the equations said more. They predicted electromagnetic waves could exist at any frequency, not just visible light. There should be invisible waves carrying energy through space that no human had ever detected. Radio waves, microwaves, X-rays, an entire spectrum of radiation predicted by 4 equations. Nobody could test this for 22 years. Heinrich Hertz finally generated and detected radio waves in 1887 at the Technische Hochschule in Karlsruhe, using a spark gap transmitter and a simple loop antenna across the room. He demonstrated that these waves reflected, refracted, polarized, and interfered exactly like light, confirming they were electromagnetic waves at a different frequency. Maxwell died in 1879 and 48 of abdominal cancer. He never saw the confirmation. 22 years between the math and the measurement. And Hertz said something afterward that I spent 3 hours one night tracking down, because I could not believe a bench experimentalist had said something this metaphysical. But he did. Hertz said, "It is impossible to study this wonderful theory without feeling as if the mathematical equations had an independent life and intelligence of their own, as if they were wiser than ourselves, indeed wiser than their discoverer, as if they gave forth more than he put into them. Let that sit for a moment. Hertz, who had just confirmed the equations by turning them into physical radio waves bouncing off metal plates, described those equations as having a life of their own, as being wiser than the man who wrote them, as giving more than was put in. This is not mysticism from a philosopher. This is a bench experimentalist describing what it felt like to watch an equation be right about something its creator never imagined. I want to stay with that Hertz quote for a moment longer because I think it is more important than almost anything else in this story. Hertz used the word wiser, not more accurate, not more powerful, wiser, as if the equations possess a form of understanding that exceeds human understanding, as if the mathematician has access to information about the physical world that the mathematician does not. This is an experimentalist, trained to distrust anything that cannot be measured, describing his experience of confirming a mathematical prediction in language that sounds like someone encountering an intelligence. And you find this same reaction again and again from the people who have worked most closely with the mathematics of physics. Eugene Wigner said the miracle of the appropriateness of the language of mathematics is a wonderful gift which we neither understand nor deserve. Paul Dirac said God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. Roger Penrose has written that mathematical truth is something that goes beyond mere human invention, that it has a kind of reality that is independent of the physical world and independent of the human mind. These are not mystics. These are physicists and mathematicians at the absolute peak of their field, and when they try to describe their experience of working with mathematics, they reach for language that sounds religious, not because they are being imprecise, but because the precision of their field experience has taken them to a place where ordinary language fails. Murray Gell-Mann stood at a blackboard at CERN in July of 1962 and predicted a particle no one had ever observed. He had organized the known baryons into a pattern using SU3 group symmetry, what he called the eightfold way. And there was a gap, a missing corner in the decouplet. The math demanded a particle with mass approximately 1680 mega-electron volts, charge -1, spin 3/2, strangeness -3. He sketched its expected decay chain on a napkin at lunch for the experimenters at Brookhaven. In February 1964, they found it, the omega minus baryon, mass 1672.5 mega-electron volts, within 0.5%. The group theory Gell-Mann used, SU3 Lie groups, was developed by Sophus Lie in the 1870s for purely mathematical purposes, studying the symmetries of differential equations. Galois had coined the concept of a group around 1830, solving problems about polynomials, abstract algebra, no physics, and it encoded the internal structure of every subatomic particle. Then general relativity, Einstein's field equations of November 1915, predicted gravitational lensing, that light bends around massive objects by a specific amount. Arthur Eddington confirmed this during a solar eclipse on May 29, 1919. 4 years later, the equations predicted black holes through Karl Schwarzschild's exact solution of January 1916, derived while Schwarzschild was serving on the Russian front. He died 5 months later, on May 11th, of a disease contracted in the trenches. The first direct image of a black hole was not captured until April 2019, 103 years. The equations predicted gravitational waves. LIGO detected them on September 14, 2015, at 9:50 a.m. UTC. Two black holes, roughly 36 and 29 solar masses, merging 1.3 billion light-years away. The signal was a displacement of 1 × 10 to the negative 21, smaller than 1/10,000th the diameter of a proton. 99 years after the prediction. Announced February 11, 2016. I want to add one more prediction that does not get enough attention. The Hulse-Taylor binary pulsar, discovered in 1974 by Russell Hulse and Joseph Taylor. This is a pair of neutron stars orbiting each other, and general relativity predicts they should lose energy by radiating gravitational waves, causing their orbit to decay at a very specific rate. Taylor and his colleagues monitored this system for decades, measuring the orbital decay with extraordinary precision. The observed decay matches the prediction of general relativity to within 0.2%. Not 2%, 0.2%. Over more than 30 years of continuous observation, Hulse and Taylor won the 1993 Nobel Prize. It was the first indirect evidence for gravitational waves, 21 years before LIGO detected them directly. Think about the cumulative weight of this. Gravitational lensing confirmed in 1919. The Schwarzschild solution pointing to black holes in 1916. Directly imaged in 2019. Gravitational waves predicted in 1916, indirectly confirmed in 1974, directly detected in 2015. The Hulse-Taylor pulsar decay, matching to 0.2%, frame dragging, a bizarre effect where a rotating mass drags space-time around with it, predicted by Lenz and Thirring in 1918. Confirmed by Gravity Probe B in 2011 to within 5% of the predicted value. Every prediction Einstein's math made has been confirmed, every single one across 100 years. With increasing precision, the equations knew, and the Higgs boson. In 1964, 3 independent groups predicted the Higgs mechanism. Englert and Brout published first, Higgs second, Guralnik, Hagen, and Kibble third. Higgs's paper was initially rejected by Physics Letters, whose editors at CERN judged it to be of no obvious relevance to physics. He revised it, added one sentence, predicting the massive scalar boson, and resubmitted to Physical Review Letters. On July 4, 2012, CERN announced its discovery using the Large Hadron Collider, which cost approximately €7.5 billion and involved over 10,000 scientists from more than 100 countries. Peter Higgs sat in the auditorium and wiped a tear from his eye. He said, "It is very nice to be right sometimes." The institution that rejected his paper spent €7.5 billion confirming it. 48 years between the math and the measurement. I want to stay with the Higgs story because the human details are extraordinary and not widely known. Peter Higgs was a quiet, almost reclusive man. He did not own a television. He did not use email. When he was told in 2012 that the boson had been found, a former colleague had to go to his apartment in Edinburgh to deliver the news in person because there was no other way to reach him. He had spent 48 years waiting, not loudly, not dramatically, just quietly in Edinburgh, doing his physics, while the rest of the world built a 27-kilometer ring of superconducting magnets underneath the Swiss-French border to check his math. There is a detail about the original rejection that I think is significant. His first paper was 2 pages long. The editors turned it down because it did not demonstrate obvious relevance to physics. A paper that predicted a fundamental particle, one that gives other particles their mass, one that completes the standard model, and the editors of a physics journal said it was not relevant to physics. Higgs later said he was indignant. The difference between obscurity and a Nobel Prize was 1 sentence. The sentence he added predicting the observable boson. What makes this painful is that the Higgs mechanism is not an optional decoration on the standard model. Without it, the W and Z bosons have no mass. Without mass for those bosons, the weak nuclear force has infinite range instead of the tiny range we observe. Without that short range, nuclear physics collapses. Stars do not form. Chemistry does not work. You do not exist. The mass of the Higgs boson is, in a very literal sense, the reason complex matter exists in the universe, and the paper predicting it was rejected for lacking relevance. The cost of confirmation was staggering. The Large Hadron Collider tunnel is 27 kilometers in circumference, crossing the Swiss-French border 4 times. The machine accelerates protons to 99.999991% of the speed of light. It generates 40 million particle collisions per second. Atlas, one of the 2 main detectors, is 46 meters long, 25 meters in diameter, and weighs 7,000 tons. All of this, every magnet, every sensor, every line of software, every career spent building and operating the machine, existed because a 2-page paper in 1964 said a particle should be there. The math spoke. 48 years and 7.5 billion euros later, humanity finally had the instrument precise enough to hear what it said. Each of these cases is extraordinary, an equation predicting the existence of something no one has observed and being right. But you could argue that this is just physics working as intended. You build mathematical models for physical phenomena, and good models make predictions. The math was designed for physics, so it works for physics. That argument holds until you look at what comes next, because the deepest cases are not cases where physicists build math for physics. They are cases where mathematicians build mathematical structures for no reason at all, driven purely by curiosity and aesthetics, with zero physical intent, and those structures turned out to be the fundamental language of reality decades or centuries later. These are the cases that should keep you up at night. In 1545, Gerolamo Cardano was trying to solve cubic equations. His method forced him to take the square root of negative numbers. He called working with them mental torture. Raphael Bombelli in 1572 showed these impossible numbers could produce real results. René Descartes in 1637 coined the derogatory term imaginary. Even Leonhard Euler, who standardized I for the square root of -1 and derived e to the I pi plus 1 equals 0, wrote that imaginary numbers exist only in imagination. Gauss in 1831 introduced the term complex number and pointed out that if they had been called lateral units instead of imaginary, there would hardly have been any scope for such obscurity. For centuries, nobody believed these numbers corresponded to anything real. Then, in 1926, Schrödinger wrote the fundamental equation of quantum mechanics. And there, in the equation, is I, the imaginary unit, not as a convenience, not as a trick you can factor out, as a structural necessity. IH bar times the partial derivative of psi with respect to time equals H hat psi. Schrödinger himself was uncomfortable. He wrote to Lorentz on June 6, 1926, calling the use of complex numbers unpleasant and directly to be objected to. For nearly a century, physicists debated whether complex numbers were genuinely necessary or just a mathematical shorthand. Could you reformulate quantum mechanics using only real numbers? In 2021 and 2022, experiments settled this definitively. Teams in China and Austria independently demonstrated that real number formulations of quantum mechanics cannot reproduce the predictions that complex number quantum mechanics makes, and which experiments confirm. They ruled out real number quantum mechanics by 43 standard deviations. That is not borderline. That is as confirmed as anything in physics has ever been. I have been obsessed with this specific example for longer than I probably should admit, because it is the one that breaks every comfortable explanation. 1545, mental torture. 1637, imaginary 2022, confirmed as necessary for reality by 43 standard deviations. 381 years. The universe was running on complex numbers for 14 billion years before anyone gave the square root of -1 a name. And for 381 years after that, humans denied they were real. There is a deeper layer to the complex number story that I think is important. The 2021 and 2002 experiments did not just show that complex numbers are convenient for quantum mechanics. They showed that any formulation of quantum mechanics using only real numbers produces different predictions than the standard complex formulation. And reality matches the complex version. The experiments used entangled photon pairs and a Bell-like inequality that distinguishes between real and complex quantum theories. The result was not close. 43 standard deviations is a number so far beyond the threshold for statistical significance that calling it significant is almost comical. In particle physics, a 5 sigma result, about 5 standard deviations, is the gold standard for a discovery. The complex number result is more than 8 times that. What this means, philosophically, is profound and largely undigested. The square root of -1 is not a mathematical convenience, it is a structural feature of reality. An object that was invented as a computational trick to solve polynomial equations. That was called mental torture. That was labeled imaginary, that mathematicians and physicists debated about for centuries, turns out to be woven into the fabric of nature at its most fundamental level. Not approximately, not as a useful fiction. Necessarily, the universe requires imaginary numbers. You cannot describe quantum mechanics without them. And quantum mechanics describes everything. If you are a formalist, this is a nightmare. If math is just symbol manipulation, why does reality care which symbols you use? Why does the universe distinguish between real number formulations and complex number formulations? If the symbols are arbitrary, the choice should not matter, but it does. The universe has preferences about which mathematics describes it, and it prefers the mathematics that includes the square root of -1. Bernhard Riemann delivered his habilitation schrift at Göttingen on June 10, 1854, on the hypotheses which lie at the foundations of geometry, purely mathematical. He extended Gauss's work on curved surfaces into n-dimensional spaces. Riemann died of tuberculosis in 1866 at 39. His lecture was published posthumously in 1868. For half a century, it sat in libraries, a beautiful piece of abstract mathematics describing curved spaces nobody needed. Then, in July of 1912, Einstein had the physical insight for general relativity. Gravity is not a force, but the curvature of spacetime. But he could not write the math. He went to Marcel Grossmann and said, "Grossmann, you have got to help me or I will go crazy." Grossmann pointed him to Riemann's geometry and to the tensor calculus of Ricci Curbastro and Levi Civita. The framework Einstein needed had been sitting in a library for 61 years, built by a man who had no idea physics would ever need it, who died a decade before Einstein was born. Einstein later wrote, "Only the genius of Riemann, solitary and uncomprehended, had already won its way by the middle of the last century to a new conception of space, solitary and uncomprehended." He built the geometry of the actual universe, and nobody noticed for 61 years. What makes the Riemann story even more extraordinary is that it was not a matter of Einstein simply plugging in Riemann's formulas. Einstein had to learn differential geometry essentially from scratch. Between 1912 and 1915, he went through what has been described as the most intense intellectual struggle in the history of physics. He made multiple false starts. He published a flawed version of his field equations in 1913, the Entworth theory, that he spent 2 years defending before realizing it was wrong. He corresponded with the mathematician David Hilbert, who was independently working on gravitational field equations, and there remains a priority dispute about who reached the correct equations first, though the physical interpretation was undeniably Einstein's. The point is that the mathematics did not make the physics easy. Riemannian geometry was available, but applying it to physics required years of grinding work. The math was sitting there, ready, correct, and complete, but it took one of the greatest minds in history 3 years to figure out how to use it, which raises a question. If mathematics is a human invention, why would a mathematical structure invented in 1854 be so difficult for the greatest physicist alive to apply to physics 60 years later? If humans invent math to solve problems, why would the solution be sitting in a library for 6 decades, unrecognized, requiring years of effort to connect to the problem it was built to solve? That is not how invented tools work. You build a tool for a purpose and then use it. You do not build a tool, forget what it is for, file it in a library, and then spend 3 years of desperate effort figuring out that it solves a problem you did not know existed when you built it. Then knot theory, which I personally think has the most perfect irony. Lord Kelvin proposed in 1867 that atoms are knotted vortex rings in the luminiferous ether. Tate began cataloguing knots systematically in the 1870s and 80s. When Kelvin's theory was abandoned and the ether discredited, the physical motivation for knot theory vanished. It continued as pure mathematics for over a century. Alexander's polynomial in 1928, Riedmeister moves in 1927, the Jones polynomial in 1984, earning Vaughan-Jones the Fields Medal. Then in 1989, Edward Witten showed that 2 + 1 dimensional quantum field theory naturally generates the Jones polynomial. Knot theory was back in physics, and separately, biologists discovered that DNA topology, the way strands link and twist inside cells, is described by knot-theoretic mathematics. Enzymes called topoisomerases perform exactly the cutting and passing operations that not theorists study abstractly. Born from a wrong physics theory, abandoned by physics, pure math for 120 years, then returning to physics and biology simultaneously, as if the math knew where it was going and was waiting for everyone else to catch up. And then, group theory, the whole arc. Galois coined group around 1830. Abstract algebra. Through the 19th century, Cauchy, Cayley, and Lee extended the theory. When Wigner and Weyl applied group representations to quantum mechanics in the 20s and 30s, physicists were hostile. They called it the Gruppenpest, the group plague. John Slater described a feeling of outrage at the incursion of abstract algebra into physics. Physicists did not want to learn an entirely new branch of mathematics that appeared to have nothing to do with the physical world, and they resented the implication that their field required it. Wigner's 1931 book, Group Theory, and its application to the quantum mechanics of atomic spectra was largely ignored for years. He later recalled that a colleague told him, to his face, that his work was useless. Think about what that means. The man who would go on to write the most famous essay in physics about the unreasonable effectiveness of mathematics was told at the beginning of his career that the mathematics he was bringing to physics was useless. The very same group theory that the physics community rejected as an unwanted abstraction became within decades the organizing language of all particle physics. Von Neumann told Wigner the critics were old fogies, and in 5 years every student would learn group theory as a matter of course. He was essentially right. By the 70s, the entire standard model was built on the gauge symmetry group U1 times SU2 times SU3. Every fundamental force in the universe described by an abstract algebraic structure that a 20-year-old invented the night before he died in a duel. 140 years from Galois to the standard model. And I should mention matrix algebra because the timeline there is equally striking. In 1855, Arthur Cayley published a foundational paper on matrix theory. Matrices were an algebraic curiosity, a way of organizing numbers into rectangular arrays and defining operations on them. Nobody needed them for anything physical. Then, in 1925, Werner Heisenberg formulated the first complete version of quantum mechanics, and it was written entirely in matrices. He called it matrix mechanics. The rules for multiplying matrices, rules that Cayley had worked out 70 years earlier for their own sake, turned out to be the rules for combining physical measurements of quantum systems. Heisenberg did not even know he was using matrices. Max Born recognized the mathematical structure and told him. The tools had been waiting for 7 decades. The timeline is staggering. Complex numbers, 381 years. Riemannian geometry, 61 years. Group theory, roughly 140 years. Matrix algebra, about 70 years. Knot theory, about 120 years. In every case, mathematicians built structures for no physical reason at all. And in every case, the universe turned out to need them. This is the pattern that breaks the comfortable explanation. You were taught math is a tool humans invented to describe nature, like a sophisticated hammer. But a hammer does not sit in a drawer for 61 years and turn out to be exactly what you need for gravity. A hammer does not get invented in the 16th century as mental torture and turn out to be structurally necessary for quantum mechanics 381 years later. That is not what tools do. Now, I know the counter-argument. Selection bias. We remember the math that found applications and forget the math that did not. There is math that so far has no known physical use. Higher transfinite cardinals. Some algebraic topology. The counter-argument is fair. But the rebuttal is devastating, and it was made by Mark Steiner in 1998. Steiner pointed out that mathematicians use mathematical beauty, symmetry, and elegance as a guide for discovering physical laws. And it works. It should not, but it does. The universe is, as Steiner put it, user-friendly to mathematical investigation in a way that has no explanation. And here is the misconception I need to flag, because it is one of the most widespread in this entire subject. The common framing, is math discovered or invented, is the wrong question. It assumes two options that are mutually exclusive. You either discover math like a continent or invent it like a telephone. But the actual landscape of positions is far more complex, and the most interesting answers reject the binary entirely. There are people who think the question is meaningless. People who think the answer is both, in different senses. People who think something stranger than either is happening. And the fact that the best minds in philosophy have fought about this for 100 years without consensus is itself evidence that the question goes deeper than anyone expected. And if you stare at the evidence long enough, something begins to emerge. If math built for pure beauty keeps describing physics, the universe may be selecting for mathematical structure. Beauty in equations correlates with truth about nature in ways nobody can explain. What if the question is not, why does math describe reality? But what if there is nothing else to describe? We will come back to this, and when we do, you will understand why I set it aside earlier. The oldest answer is Platonism, and it is also the most radical, which is funny because people treat it as the boring default. Platonism says mathematical objects, numbers, structures, relationships exist independently of human minds. They are not invented. They are discovered. They exist in an abstract realm that is not physical and not mental. And mathematicians access this realm through something like intellectual perception. Plato proposed this 2,400 years ago. And you might think it sounds like ancient mysticism that modern thinkers have moved past. You would be wrong. Some of the most brilliant mathematical minds of the 20th century were committed Platonists. Kurt Gödel was the most important logician since Aristotle, and I do not use that phrase casually. In 1931, at 25, he published two theorems that shattered the foundations of mathematics and changed the philosophy of knowledge permanently. His first incompleteness theorem proved that in any consistent formal system powerful enough to express basic arithmetic, there exist statements that are true but cannot be proved within that system. His second proved that such a system cannot prove its own consistency. I need to flag a widespread misunderstanding here, because these theorems are among the most misrepresented results in all of science. You have probably heard them summarized as, there are things we cannot know, or math is incomplete, or math is broken. None of that is quite right. What Gödel actually proved is something more specific and more disturbing. He proved that truth outruns provability. For any formal system strong enough to contain arithmetic, there are true statements that the system cannot derive from its axioms. The system is not broken. It is not defective, but it cannot see all of its own truths from within. The map is necessarily smaller than the territory, no matter how large you make the map. This is not a limitation of human cleverness. It is a theorem about mathematical structures themselves. Even a perfect computer, running forever, could not do what Godel proved cannot be done. And Godel drew from this a philosophical conclusion that most of the mathematical community preferred to ignore. He was a fierce Platonist from about 1925 onward. He believed mathematical objects really exist, independently of human minds, and he saw his incompleteness theorems as evidence for this belief. His reasoning was direct. If mathematical truth cannot be captured by any formal system, then truth must be something real, something objective, something that exists independently of our formal tools. You cannot have truths that transcend all formal systems unless those truths exist in some realm beyond formal systems. And that realm, Godel believed, is the Platonic mathematical world, which humans access through a faculty of mathematical intuition analogous to sense perception. Roger Penrose, the Nobel Prize-winning physicist, holds a similar position. He proposes a three-world model: the Platonic mathematical world, the physical world, and the mental world, connected by three mysteries. He has written that to him, the world of perfect forms is primary, its existence almost a logical necessity, and both the other two worlds are its shadows. Penrose uses Godel's theorems to argue that human mathematical understanding is non-algorithmic, that consciousness accesses truth beyond what any formal system or computer can reach. The strongest arguments for Platonism include the Quine-Putnam indispensability argument, which says that mathematical entities indispensable to our best scientific theories must be accepted as existing. There is also the sheer objectivity of mathematical truth. Nobody chooses whether the Pythagorean theorem is true. It is true, and it was true before any human being thought of it, and it would be true if humans had never existed. And there is Wigner's puzzle itself. Platonism explains the unreasonable effectiveness perfectly. Math works because we are discovering real features of an independently existing mathematical realm that the physical world participates in or is structured by. But Platonism has a problem, and it is devastating. Paul Dirac stated it precisely in 1973. If mathematical objects are abstract, existing outside space and time, causally inert, then how on earth do humans know about them? We know about physical objects because they interact causally with us. Light bounces off a table, hits your retina, and you perceive the table. Gravitational waves stretch a detector, and we perceive them. But the number 7 does not bounce off anything. It does not emit mathematical light. If Platonic objects have no causal powers and exist outside space and time, there is no mechanism by which a physical brain could access them. Platonism explains why math works, but cannot explain how we discover it. It answers the big question and immediately creates another one just as hard. So maybe math is not real. Maybe it is just a game of symbols. That was David Hilbert's position. Formalism. Mathematics is the manipulation of symbols according to rules. The symbols do not refer to anything. They are marks on paper. Hilbert was arguably the most influential mathematician alive at the turn of the 20th century, and his program, formulated around 1921, aimed to formalize all of mathematics in complete and consistent axiomatic systems, prove their consistency using the most restrictive possible methods, and demonstrate that every mathematical statement could be either proved or disproved. Mathematics would be rendered self-certifying, self-contained, and complete. Hilbert's rallying cry was "Wir müssen wissen, wir werden wissen." We must know, we will know. He delivered this on September 8, 1930, at a congress in Königsberg. The words are engraved on his tombstone. And here is the single cruelest irony in the history of mathematics. The day before Hilbert spoke, September 7th, 1930, at the very same conference, a 24-year-old Kurt Gödel had quietly announced his first incompleteness result at a round-table discussion. Hilbert was apparently not in the room. When the full paper was published in 1931, Hilbert was reportedly furious. The dream of complete, self-certifying, decidable mathematics was dead. Gödel had proved, using mathematics itself, that mathematics cannot do what Hilbert wanted it to do. The builder's greatest tool was turned against the builder's greatest project. And formalism has an even bigger problem for our purposes. If math is just symbol pushing, if the symbols do not refer to anything real, then why does pushing those symbols around on paper tell you that a positron exists before you detect one? Why does symbol manipulation predict gravitational waves 99 years in advance? If math is a game without meaning, why does the universe play by the same rules? L.E.J. Brouwer, born 1881, founded intuitionism. Mathematics, he argued, is a free creation of the human mind, grounded in what he called the primordial intuition of time. Mathematical objects do not exist until a human mind constructs them. A proof is not a demonstration that something is true. A proof is a construction, and if you cannot construct it, it does not exist. This meant Brouwer rejected the law of excluded middle for infinite domains. You cannot say, either this infinite sequence has property P or it does not, unless you can construct a proof one way or the other. For finite sets, fine. For infinite ones, you are making a claim about a completed infinity that no mind has constructed, and Brouwer refused to accept it. Hilbert was livid. He said, taking the principle of the excluded middle from the mathematician is the same as prohibiting the boxer the use of his fists. The Brouwer-Hilbert controversy consumed the 1920s. In 1928, Hilbert orchestrated Brouwer's removal from the editorial board of Mathematische Annalen, the most prestigious math journal in the world. The episode was called The War of the Frogs and the Mice. Even Hermann Weyl, one of Hilbert's most brilliant students, was temporarily won over by Brouwer in 1921, which alarmed Hilbert deeply. Brouwer was personally devastated by the expulsion and never fully recovered. But intuitionism has the same vulnerability. If math is a human mental construction, why does a universe that existed for 14 billion years before any human mind arose obey it? Why would the free creations of minds that appeared in the last few 100,000 years correspond to the structure of a cosmos that predates them? Structuralism, championed by Stuart Shapiro and Michael Resnick in the 1990s, tries to split the difference. Mathematics is about structures and patterns, not individual objects. Numbers have no intrinsic properties. They are defined entirely by their roles within a structure, by their relationships to each other. This resolves some headaches, particularly what is called Benacerraf's identification problem. The fact that there is no unique, correct way to define the natural numbers using sets. But it pushes the central question backward without answering it. If math is about structures, why does the physical world exhibit these particular structures? Why is the universe structured mathematically? Ruben Hirsch, in his 1997 book, What is Mathematics? Really proposed what he called humanism. Math is a social, cultural, historical phenomenon. Mathematical objects are mental constructs shared by a community. They gain a kind of objectivity from social consensus, but they do not exist in any Platonic realm. This is the least metaphysically expensive position, and it is also the one that does the worst job with Wigner's puzzle. If math is a social convention, like traffic laws or table manners, then its effectiveness in predicting antimatter and gravitational waves is a flat-out miracle. Why would social conventions describe the behavior of quarks? And then Mark Balaguer, in his 1998 book Platonism and Anti-Platonism in Mathematics, reaches what I think is the most intellectually honest and most disturbing conclusion in the entire debate. He argues that both full-blooded Platonism and fictionalism are defensible positions, and that there could never be good reason to favor one over the other. His full-blooded Platonism says that all logically possible mathematical structures exist. Every consistent mathematical theory describes real objects in some mathematical realm. This solves the access problem, because if every consistent theory is true of something, you do not need a special causal connection to discover truths. Any consistent theory you write down will be true of some mathematical reality. But think about what that means. If every consistent mathematical structure exists, and the physical world is one of those structures, then we live inside mathematics, and we would have no way of knowing this from the inside. Every position fails. Every explanation of why math works this well either begs the question, collapses into contradiction, or leads to conclusions more disturbing than the original puzzle. The best minds in philosophy have spent over a century on this and have not resolved it. They have made the problem worse. Each new attempt to answer reveals that the question goes deeper than the previous generation realized. The authorities have no answer. And I want to point out something about this philosophical failure that I think is significant. It is not that the thinkers are not brilliant. They are. Godel, Benacerraf, Quine, Putnam, Field, Shapiro, Balaguer. These are some of the sharpest minds in the history of analytic philosophy. The failure is not a failure of intelligence. It is a failure that might be structural. Every attempt to explain why math works ends up either using math in the explanation, which is circular, or gesturing at something beyond math, which nobody can define. Hilary Putnam, one of the most important philosophers of the 20th century, wrote that realism is the only philosophy that does not make the success of science a miracle. But he could not explain what makes mathematical realism true. Hartree Field, in his 1980 book Science Without Numbers, tried to show that Newtonian gravity could be reformulated without mathematics at all. He succeeded, sort of, but only by replacing numbers with geometric structures that look suspiciously like mathematics under a different name. You cannot get away from it. Every time you try to step outside mathematics to explain mathematics, you find more mathematics underneath. Mario Livio, the astrophysicist, wrote a book in 2009 called Is God a Mathematician? And reached what I think is the most honest, popular conclusion anyone has offered. He said, mathematics is partly invented and partly discovered. We invent the concepts, but then we discover the relationships between them, and those relationships turn out to correspond to the structure of the physical world. Some people find this a deeply unsatisfying answer. Livio himself acknowledged that some would consider his conclusion inconclusive, but I actually think the inconclusiveness is the point. The question may not have a clean answer. It may not have any answer at all, at least not one expressible within the system. So instead of asking what math is, I want to ask what math does to the people who get closest to it. Because there is a pattern in the biographies, and it is not subtle, and it is not coincidental. Georg Cantor was born March 3rd, 1845, in St. Petersburg. He proved in December of 1873 that the real numbers cannot be put into one-to-one correspondence with the natural numbers. There are more real numbers than counting numbers. Infinity comes in sizes. This shattered 23 centuries of mathematical thought. From the Greeks onward, infinity was one thing. Cantor proved it is many things, an infinite hierarchy of infinities, each larger than the last. His diagonal argument, published 1891, is considered one of the most elegant proofs in all of mathematics. With a technique a bright undergraduate can follow, he proved that no list of real numbers can ever be complete. You can always construct a number not on the list. Leopold Kronecker, one of the most powerful mathematicians in Germany, despised Cantor's work with a fury that went beyond professional disagreement into personal persecution. Kronecker declared, "God made the integers. All else is the work of man." He called Cantor a scientific charlatan, a renegade, a corrupter of youth. He blocked publication of Cantor's work in the leading journal, and is widely believed to have prevented Cantor from ever obtaining a position at the University of Berlin, the most prestigious appointment in German mathematics. Henri Poincaré called set theory a grave disease infecting the discipline. Cantor's first serious mental breakdown came in the summer of 1884. He was hospitalized. He became obsessed with proving that Francis Bacon wrote Shakespeare's plays. From 1900 onward, he spent increasingly long stretches in the Nerven Clinic in Halle, sometimes months at a time. His youngest son Rudolf died suddenly in 1899. In June of 1917, he entered the sanatorium for the last time, involuntarily writing letters to his wife begging to come home. He died of a heart attack on January 6, 1918, during World War I, in poverty and isolation. David Hilbert's response to those who would reject Cantor's creation became one of the most quoted lines in mathematics. "No one shall expel us from the paradise that Cantor has created." Set theory became the very foundation of modern mathematics. The man who built it died in an asylum. And Godel, we have already seen his theorems and his philosophy, but his end demands its own accounting. Because the irony is almost too precise to be real. Godel developed severe paranoid tendencies that worsened over decades. He feared being poisoned. He feared refrigerator gases. He wore heavy winter clothing in summer. He would eat only food prepared by his wife, Adele, the only person in the world he trusted. At Princeton, his friendship with Einstein anchored his daily life. They walked together every day for years, conversing in German. Einstein warm and gregarious, Godel solemn and suspicious. Oscar Morgenstern reported that Einstein said his own work no longer meant much, that he came to the Institute merely for the privilege of walking home with Godel. Freeman Dyson observed that Godel was the only colleague who walked and talked on equal terms with Einstein. In 1949, Godel presented Einstein with a birthday gift that might be the most extraordinary gift in the history of science. He had found a new exact solution to Einstein's field equations, the Godel metric, describing a rotating universe with closed time-like curves. Time travel is logically possible within general relativity. The physicist had not seen this in his own equations. The logician had, As Jim Holt observed, Godel, a logician, had done something that was beyond even Einstein's abilities. When Adele was hospitalized after a stroke in late 1977, Godel stopped eating. There was nobody he trusted to prepare his food. He died on January 14th, 1978, weighing approximately 65 pounds. The death certificate read, "Malnutrition and inanition caused by personality disturbance. The greatest logician since Aristotle. The man who proved that formal systems cannot fully comprehend themselves from the inside. Destroyed by an irrational fear that no formal logic could reach. The mind that demonstrated the limits of self-knowledge could not know its own illness. If you wrote this as fiction, nobody would publish it. The parallel is too on the nose. The system could not see its own flaw." There is one more detail about Gödel's final years that I think deserves attention. After Einstein died in 1955, Gödel lost the one person who had truly understood him. The daily walks stopped. His isolation deepened. He continued working, producing results in set theory and philosophy, but the social anchor was gone. His later philosophical writings reveal a mind increasingly certain that mathematical Platonism was true and increasingly unable to communicate why. He wrote about mathematical intuition as a form of perception, comparing it to sight. He argued that just as we perceive physical objects through our senses, we perceive mathematical objects through a faculty of the mind that is equally real but less understood. He believed that the reason Hilbert's program failed was not that mathematics is defective, but that mathematics is too rich, too vast, too real to be captured by any single formal system. The incompleteness theorems were, for Gödel, proof that mathematical reality exceeds human formalization. Not a disappointment, but a confirmation of Platonism. And then this mind, this instrument of perhaps the most profound logical reasoning in human history, was undermined by a delusion it could not analyze. He could evaluate the logical consistency of rotating universes and closed, time-like curves. He could prove theorems that the greatest mathematicians of his generation could not refute. But he could not evaluate the irrationality of his own fear of being poisoned. The formal system of his mind contained a flaw it could not see. The parallels to his own theorem are so exact, they feel like they were designed as if the universe were making a philosophical argument using a human life as the proof. Srinivasa Ramanujan was born December 22nd, 1887, in Erode, Tamil Nadu, into poverty. He had virtually no formal mathematical training beyond some textbooks. He attributed his mathematical discoveries to the goddess Namagiri Taya. He described visions while sleeping, a red screen formed by flowing blood, and a hand writing formulas upon it. Elliptic integrals. He said, "An equation for me has no meaning unless it expresses a thought of God." On January 16th, 1913, he sent a letter to G.H. Hardy at Cambridge containing roughly 120 results, most without proofs. Hardy initially suspected it was a prank. Then he and Littlewood examined the formulas carefully, and Hardy concluded that they must be true, because if they were not true, no one would have the imagination to invent them. Hardy called receiving that letter the one romantic incident in his life. He rated mathematicians on a scale to 100. Himself, 25, Littlewood, 30, Hilbert, 80, Ramanujan, 100. The taxicab story is famous, but the real story behind it is not. Hardy visited the ailing Ramanujan and mentioned his taxi was number 1729, which he called rather dull. Ramanujan replied instantly that it is a very interesting number, the smallest expressible as the sum of 2 cubes in 2 different ways, 1 cubed plus 12 cubed and 9 cubed plus 10 cubed. This sounds like a party trick. But Ken Ono's 2015 research revealed that Ramanujan was actually using 1729 and related numbers to develop mathematics for K3 surfaces, work that researchers today still find challenging. In his last letter to Hardy, January 12, 1920, 3 months before his death, Ramanujan describes 17 examples of what he called mock theta functions. Nobody understood them. It took over 80 years. In 2002, Sanders Weggers identified them as parts of harmonic, weak mass forms, and it turned out these functions provide the mathematical framework for calculating black hole entropy. A dying man with no formal training, attributing his formulas to a goddess, writing down functions that describe the thermodynamics of objects that would not be theoretically understood for another 50 years. His relatives boycotted his cremation, believing he had sinned by crossing the oceans. He died April 26, 1920, at 32. His 3 notebooks contain nearly 3,900 results, almost all since verified. Littlewood said, every positive integer was one of Ramanujan's personal friends. There is one more thing about Ramanujan that I want to mention because it connects directly to the central question of this video. Ramanujan produced results. He did not, in general, produce proofs. He wrote down formulas and said they were true. Hardy, who was one of the most rigorous mathematicians of his generation, a man who insisted on proof above all else, was driven nearly mad by this. Ramanujan would state a result, and Hardy would ask for the proof, and Ramanujan would say something like, "It came to me," or refer to the goddess. And yet, the results were correct, almost without exception. Every formula Ramanujan wrote down turned out to be true, not approximately true, not true under certain conditions, true. How, if mathematics is a human invention, a social construction, a formal game, then Ramanujan should not have been able to do what he did. He had no access to the social construction. He had not been trained in the formal game. He was working in near total isolation in South India with a couple of textbooks, and he produced results that the most trained, most sophisticated, most socially embedded mathematicians of his time could not produce. His work was not just correct, it was decades ahead of its time. Mock theta functions in 1920, understood in 2002. K3 surfaces in the taxicab number, recognized in 2015. He was accessing mathematical truths that the mathematical community would not reach by its own methods for 70 or 80 years. Either Ramanujan was somehow inventing mathematics that perfectly matched truths nobody would discover for decades, which would require a form of precognition about where mathematics was heading, or he was discovering mathematics, accessing truths that already existed and that the community would independently verify much later. The first option requires something close to a miracle. The second option requires Platonism to be true. Neither is comfortable. Emmy Noether proved what Lederman and Hill called certainly one of the most important mathematical theorems ever proved in guiding modern physics. Noether's theorem, presented July 26, 1918, establishes that every continuous symmetry of a physical system corresponds to a conservation law. Time symmetry yields conservation of energy. Spatial symmetry yields conservation of momentum. Rotational symmetry yields conservation of angular momentum. This is not a result derived from physical observation. It is a mathematical theorem that turned out to describe the deepest structural fact about the physical universe that we have ever found. When Hilbert and Klein invited her to Göttingen in 1915, faculty objected. What would their soldiers think returning from war to learn at the feet of a woman? Hilbert responded, "I do not see that the sex of the candidate is an argument against her admission. After all, we are a university, not a bathing establishment." She spent 4 years lecturing under Hilbert's name because the university would not let her teach under her own. When finally given a position, she was specifically denied pay. Whale said he was ashamed to occupy a preferred position beside her, knowing she was his superior as a mathematician in many respects. Fired by the Nazis in 1933 for being Jewish, she emigrated to Bryn Mawr and died of surgical complications on April 14, 1935, at 53. Einstein wrote to the New York Times that in the judgment of the most competent living mathematicians, she was the most significant creative mathematician since the higher education of women began. I want to dwell on Noether's theorem for a moment longer, because I think it is the single most underrated result in the entire history of physics, and I include general relativity and quantum mechanics in that assessment. Here is why. Every conservation law you have ever heard of, conservation of energy, conservation of momentum, conservation of angular momentum, conservation of electric charge, every single one is a consequence of a symmetry. And Noether proved this, not as a physical observation, but as a mathematical theorem. The connection between symmetry and conservation is not something we discovered by doing experiments. It is a mathematical necessity. If the laws of physics do not change over time, energy is conserved. That is not an empirical finding. That is a logical consequence of time translation symmetry, proved by Noether. What this means is that the most fundamental regularities of the physical world, the things we call conservation laws, are not brute facts about nature. They are mathematical consequences of symmetries, and symmetries are mathematical structures. So the most basic features of physics are, at their root, mathematical theorems, not descriptions of what happens, explanations of why it must happen. Mathematics is not modeling nature here. It is revealing the architecture of nature. And the woman who proved this was not allowed to teach it under her own name for 4 years. Évariste Galois invented group theory at roughly 18. His manuscripts were lost or rejected 3 times, sent to Cauchy, who mishandled them, sent to Fourier, who died with the manuscript in his possession, reviewed by Poisson, who declared them incomprehensible. His father committed suicide after a political dispute. On the night of May 29, 1832, Galois stayed up, writing his mathematical testament. He was 20 years old. He had been imprisoned for political activism. He had been challenged to a duel, and the circumstances remain murky. Some historians believe it was over a woman. Others suspect a political setup. What is not murky is what he did with his last night. He wrote mathematics feverishly, desperately. He condensed an entire theory into a handful of pages, a theory that nobody alive could understand, scrawling in the margins notes like, "There is something to complete in this demonstration, and I do not have the time." Whale later called this letter perhaps the most substantial piece of writing in the whole literature of mankind. Not the most elegant, not the most polished, the most substantial. The next morning, he was shot in the abdomen in a duel. He was found by a peasant and taken to a hospital. No surgeon was summoned. His last words to his brother Alfred: "Do not weep, Alfred. I need all my courage to die at 20. He died May 31st, 1832, of peritonitis, the day after the duel. He was buried in a common grave. Joseph Liouville published the manuscripts in 1846. 14 years later, after spending months deciphering the hasty notation, when Liouville finally understood what Galois had done, he announced it to the French Academy with undisguised astonishment. Group theory now underlies every fundamental force in the Standard Model. The symmetry group SU3 that Gell-Mann used to predict the omega minus, the gauge group that structures the entire Standard Model, the framework that organizes every known particle and interaction, all of it descends from the ideas a 20-year-old wrote down the night before he was killed. Alexander Grothendieck, born March 28, 1928, in Berlin. His father, Alexander Shapiro, was a Russian Jewish anarchist revolutionary who had participated in the 1905 revolution and spent years in prison. His mother, Hanke Grothendieck, was a German journalist and activist. When the Nazis came to power, the family scattered. His father was interned in France and then deported. He was murdered at Auschwitz in 1942. The boy was sheltered in Le Chambon-sur-Lignon, a village whose residents systematically hid Jewish children from the Nazis. He hid in the woods during raids. He was stateless for most of his life. And from this wreckage, Grothendieck produced mathematics that redefined the field. He reinvented algebraic geometry from the ground up, introducing schemes, topoi, and étale cohomology. His colleagues described his work as operating on a level of abstraction that most mathematicians could not follow. He did not solve individual problems. He rebuilt entire fields so that problems dissolved. His approach to the wild conjectures was compared to slowly raising the water level around an island until it becomes trivially submerged, rather than attacking the rock with a chisel. His work was essential to Andrew Wiles's proof of Fermat's last theorem. Decades later, he won the Fields Medal in 1966, but refused to travel to Moscow to collect it, in protest of Soviet military actions. Then in 1970, upon discovering that the Institut des Hautes Études Scientifiques received partial funding from the French military, he resigned. Immediately, completely. This was a man for whom state violence was not abstract. It had killed his father. It had defined his childhood. He could not participate, even indirectly, even symbolically. Over the following years, he drifted away from mathematics. He taught briefly at Montpellier, became involved in environmental activism, wrote a massive autobiographical mathematical memoir called Récoltes et Semailles. Over 1,000 pages of brilliance interwoven with bitterness. And then, in August 1991, he disappeared. He retreated to Le Serre, a village in the Pyrenees, and simply stopped. No running water, dandelion soup. He cut all ties with his family, his colleagues, the mathematical world that revered him. His daughter Johanna said, "Returned letters came back, return to sender." He died November 13th, 2014, at 86. Tens of thousands of handwritten pages from his years in isolation were donated to the Bibliothèque Nationale de France. Nobody has yet read them all. Paul Dirac believed God has a book containing the perfect proof for every theorem. You do not have to believe in God, but you should believe in the book. He appeared at colleagues' doors with a suitcase announcing, "My brain is open." Roughly 1,500 papers, with over 500 collaborators, making him the most prolific mathematician of the 20th century. The Dirac number, a measure of collaborative distance from him, became a kind of academic currency, a mathematical version of 6 degrees of separation. His 2 older sisters died of scarlet fever days before his birth. His mother, terrified of losing him too, kept him out of school until age 10 and barely let him out of her sight. He never learned to butter his own bread. He owned almost nothing. He gave away prize money. He lived on the road for decades, moving from one mathematical collaborator to the next, carrying everything in a battered orange suitcase. He called God the supreme fascist, children epsilons, people who stopped doing mathematics, dead, and people who actually died, left. When his friend Ron Graham bet him $500 he could not quit amphetamines for a month, Dirac won the bet and then said, "You have set mathematics back a month." He resumed immediately. He died at 83 at a mathematics conference in Warsaw, working. His epitaph, which he wrote himself, reads, "I have finally stopped getting dumber." What strikes me about Dirac is the theology of the book. He was not religious in any conventional sense. He used the supreme fascist as a half-joke, half-serious name for a God he did not claim to believe in. But the book was real to him. He genuinely believed there exists somewhere, somehow, a collection of the most elegant proofs, perfect proofs, proofs that illuminate rather than merely convince. And when he encountered a particularly beautiful proof, he would say, "That is from the book." This is Platonism expressed not as a philosophical position, but as an emotional relationship with mathematics. Dirac could not stop doing math. He could not even slow down. 70 years of continuous work, because the proofs were there, in the book, and he could feel them. These stories are not decoration. They are evidence. The people who got closest to what mathematics actually is were broken by it, rejected for it, killed for it, or driven mad by it. This is not what happens when people invent a tool. Nobody goes mad from inventing spreadsheets or internal combustion engines. This is what happens when people discover something vast and real, and their minds are not large enough to contain it. Whatever mathematics is, the biographical evidence suggests it is not something humans built. It is something humans found, and it broke them. And here is the thread that ties the biographies to the philosophy to the evidence. These people were not inventing, they were discovering, and whatever they found, it was too large for any one mind. Remember what Godel proved. A system complex enough to contain arithmetic cannot fully see its own truths from within. If what these mathematicians touched is the structure of reality itself, then the structure is, by theorem, unable to fully explain itself to any mind that is part of it, including theirs, including yours. I want to step back for a moment and look at the full arc of what we have covered, because I think the shape of it matters. We started with a number, 1.001, 159, 6521, 8059, agreement between math and reality to 12 decimal places. Then we watched that precision replicate itself across a century of physics. Antimatter predicted and found. Electromagnetic waves predicted and found. Gravitational waves predicted and found. The omega minus predicted and found. The Higgs boson predicted and found. Always the same pattern. The math speaks first. Reality confirms later. Sometimes years later, sometimes decades, sometimes a century. Then we watched something even stranger. Math that was never meant for physics. Math built for beauty, for curiosity, for the sheer pleasure of abstraction, turning out to be the language of reality. Complex numbers 381 years from mental torture to quantum necessity. Riemannian geometry 61 years from a lecture hall to the shape of spacetime. Group theory 140 years from a doomed 20-year-old's notebook to the standard model. Not theory. 120 years from a wrong theory about atoms to quantum field theory and DNA. Then we watched the philosophers try to explain it and fail. Every position collapsing, every answer generating a harder question. And then we watched the people who got closest to the answer, the ones who touched whatever mathematics really is, and we saw what it did to them. And now there is only one place left to go, the place where all of these threads converge into something that, honestly, I have been reluctant to say out loud because it sounds too large, but the evidence demands it. Which brings us to the place I have been circling since the first minute. Max Tegmark, a physicist at MIT, proposed the mathematical universe hypothesis. The external physical reality, he claims, is not described by mathematics. It is a mathematical structure, not metaphorically, literally. The universe, including you, including your thoughts, including the neurons firing in your brain as you process this sentence, is a mathematical structure. Matter is not a thing that obeys mathematical laws. Matter is what mathematical structure looks like from the inside. I want to be honest about the criticism, because it is substantial. Peter Voigt at Columbia has described the hypothesis as not so much wrong as empty. Sabine Hossenfelder asked the question I think cuts deepest. How would you distinguish a universe that is mathematics from one that is merely perfectly described by mathematics? If there is no observable difference, is the claim meaningful? These are good objections. The hypothesis may be conflating description with identity, but here is what disturbs me about dismissing it. Every single time in the history of physics that someone has said the math is just a description, the reality is something else underneath, they have been wrong. The electromagnetic field was supposed to need an ether to propagate through. There was no ether. The field was the reality. Spacetime was supposed to be a mathematical convenience for organizing events. General relativity showed spacetime is the reality. It curves, ripples, and carries energy. The wave function was supposed to be a calculation tool. Increasingly, interpretations treat the wave function itself as the fundamental thing. At every level, the scaffolding turned out to be the building. The description turned out to be the thing being described. And there is one more piece of evidence that pushes in this direction. The fine structure, constant. This is the number that governs the strength of the electromagnetic interaction. Its value is approximately 1/137, or more precisely, 0.0729735. It is a dimensionless number, meaning it is the same regardless of what units you use. It is not in meters or seconds or kilograms. It is a pure number, a pure ratio, and it determines everything about how light and matter interact. If the fine structure constant were slightly different, atoms would not form, chemistry would not work, stars would not burn, and you would not exist. Richard Feynman called it one of the greatest mysteries of physics. He said, all good theoretical physicists put this number up on their wall and worry about it. He said, it is a magic number that comes to us with no understanding by man. We know what it means. We know what it does. We do not know where it comes from. It is not derived from any deeper theory. It is not predicted by any known mathematics. It is just there, a number governing the universe. And if Tegmark is right that the universe is a mathematical structure, then the fine structure constant is not a property of a physical universe that happens to be mathematical. It is a property of the mathematical structure itself. It is a number that the structure has. The way 7 is prime, the fine structure constant is approximately 1 over 137. Not because anything caused it to be that way, because that is what the structure is. The number does not describe something. The number is something. And if Tegmark is right, or even partially right, then something follows that nobody wants to say publicly. And this is where every video on this channel converges into a single point. If the universe is a mathematical structure, then Gödel's incompleteness theorems apply to it. Feel the weight of that. Gödel proved that any formal system complex enough to contain arithmetic contains true statements the system cannot prove from within. If the universe is such a system, and it obviously is, it contains arithmetic and vastly more, then there are true facts about the universe that no being inside it can ever determine. Not because we are not smart enough, not because our instruments lack precision, not because we need more funding or better theories, because it is mathematically impossible. The limitation is structural. It is woven into the fabric of existence itself. Stephen Hawking confronted this directly in his 2002 lecture, Gödel and the End of Physics. He said we and our models are both part of the universe we are describing, making physical theory self-referential in the manner of Gödel's theorem. One might therefore expect it to be either inconsistent or incomplete. And then he said something that, coming from Stephen Hawking, should have shaken the foundations. He said some people will be very disappointed if there is not an ultimate theory that can be formulated as a finite number of principles, and that he used to belong to that camp. But he changed his mind, and the measurement problem in quantum mechanics sits right at this fracture. As we covered in the measurement problem video on this channel, the math of quantum mechanics describes everything exquisitely. The evolution of wave functions, interference, entanglement, everything except one thing. The moment you look, the moment observation collapses the wave function and probability becomes actuality. At that precise point, the equations go silent. Different interpretations tell different stories. Many worlds says collapse never happens. Copenhagen says it does, but will not define it. Cubism says the wave function is about beliefs, not reality. None of them solve the problem. The most successful mathematical framework in history has a hole in it, precisely where consciousness meets physics, as if the structure recognizes that something is observing it and cannot describe that recognition in its own language. If you watched the retrocausality and Bell's theorem video, you know it goes deeper. The block universe suggests all of time exists simultaneously. What we call observation may not be a moment of collapse, but a slice of a timeless mathematical structure encountering itself. The future shaping the past. And if you watch the quantum Zeno effect video, you know observation is not passive. It intervenes. It changes outcomes. And then there is consciousness. The hard problem, as David Chalmers defined it in 1995. Why does it feel like something to be you? You can describe every neuron, every synapse, every electrochemical signal in mathematical language. But the math does not capture the feeling, the redness of red, the ache of loss, the sensation of understanding. Consciousness is the one phenomenon we are most certain exists, because we experience it directly. And it is the one phenomenon that mathematics has never been able to describe. The most powerful descriptive tool in the history of our species hits a wall at the one thing we know most intimately. And here is the thing I keep coming back to, the thing that connects the measurement problem and the hard problem and Godel's theorems into a single, coherent shape. They are all cases where a system encounters its own boundary. In the measurement problem, the mathematical formalism of quantum mechanics encounters the act of observation, the moment where the system includes the observer and breaks down. In the hard problem, the mathematical description of the brain encounters subjective experience, the interior of the system, and fails to capture it. In Godel's theorems, a formal system encounters its own self-referential statements and cannot resolve them. The pattern is the same each time. When mathematics turns inward, when it tries to describe the thing that is doing the describing, it hits a wall. If the universe is a mathematical structure, then all three of these barriers are the same barrier. They are all instances of the structure failing to fully comprehend itself from within. The measurement problem is not a flaw in quantum mechanics. The hard problem is not a failure of neuroscience. Gödel's incompleteness is not a limitation of formal logic. They are all reflections of the same underlying fact, which is that a sufficiently complex system cannot model itself completely. The map cannot contain itself. The eye cannot see itself. And whatever the universe is, it contains us, and we are the part of the universe that is trying to understand the universe, which makes us exactly the kind of self-referential structure that Gödel proved cannot be completed. Wigner published his essay in 1960. That was 67 years ago. In that time, the precision of mathematical prediction has gotten more extreme, not less. The agreement between theory and experiment has improved by orders of magnitude. The pattern of pure mathematics, finding physical application, has continued without a single failure, and the philosophical explanation has not advanced 1 inch. Every attempt to answer Wigner's question has either restated it in fancier language or made it worse. And the people who work on this, the honest ones, the ones who have spent their careers thinking about the foundations of mathematics and physics, they know this. They know there is no answer. And they keep working anyway, because the question will not let them go. That is what mathematics does to the people it touches. It does not release them. So here is where we end, not with an answer, with the shape of the question fully revealed. Mathematics was not built to describe reality. It was built for beauty, for play, for the aesthetic pleasure of intelligent minds, with nothing practical in mind. And yet, it describes reality with a precision that nothing else in human experience matches. It predicts the existence of particles decades before they are found. It predicts the behavior of spacetime a century before we can measure it. It predicts the properties of electrons to 12 decimal places. and nobody can explain why. The people who got closest to understanding what mathematics is were destroyed by it. Cantor in the asylum, Godel starving in Princeton at 65 pounds, Ramanujan dead at 32, the goddess's formulas describing black holes a century later, Galois writing the foundations of particle physics the night before dying at 20, no other proving the deepest theorem in physics while forbidden to teach it. Grothendieck alone in the mountains for 23 years, writing. And the philosophical attempts to explain what they found have all failed. Platonism cannot explain how we access mathematical truth. Formalism cannot explain why symbol manipulation predicts antimatter. Intuitionism cannot explain why mental constructions describe a universe that predates all minds. Structuralism pushes the question backward without answering it. Every position, examined carefully, collapses. The calculations have been checked. The 12,672 Feynman diagrams have been evaluated. The electron's magnetic moment agrees with prediction to 1 part in a trillion. The complex numbers that Cardano called mental torture are confirmed as structurally necessary for reality by 43 standard deviations. The geometry that Riemann built for beauty alone is the geometry of the actual universe. The group theory that Galois wrote the night before he died is the language of every fundamental force. The mock theta functions that Ramanujan attributed to a goddess describe the entropy of black holes, and you are inside it, right now, made of the same mathematics, thinking with a brain that is itself a mathematical structure, trying to understand the mathematical structure it is part of. And Godel proved 95 years ago that this is exactly the kind of thing a sufficiently complex system cannot do. The key fits the lock. It has always fit the lock, every door, every time. And the hand holding the key cannot explain why, because the explanation, if it exists, may be one of the true things the structure cannot prove about itself.